All right, AP Calculus BC, Unit 3, Day 7. We're going to continue with parametrics and talk about derivatives of parametrics. But first, we're going to do this 4-problem warm-up. So I want you guys to try these problems yourself first. Go ahead and pause the video, and then I will go ahead and go over each of them quickly. This is very similar to yesterday's homework and also the examples we did in the lesson. So go ahead and pause the video, and then I'll go ahead and you can compare your answers to mine and jump forward if you got it right. Okay, so we're going to try and sketch it without a graphing calculator, indicate direction, initial term of points, Cartesian equation. So the same kind of stuff I've been asking you to do and you're supposed to do in your assignment. Now, I think it's best to try and get these into a Cartesian equation first. Now, all these ones that have trig, which are a lot of these, are probably going to be conic sections, parabolas, circles, hyperbolas, ellipses. And to get them together into a Cartesian equation, which has just x and y and no t's, single equation instead of two, you need to use the Pythagorean trig identity. So the one that you should have memorized very easily is sine squared plus cosine squared equals 1. The other two come from this, and I challenge you to be able to write this at least once on each homework assignment, warm-up notes, whatever, without looking it up. Because if you have to look it up, then you're not going to do well on a test or something. So then I'm going to divide these all by sine squared to get another version. Cosine over sine is cotangent. 1 over sine is cosecant squared, so that's another version. And then if you go back to the original and divide it all by cosine squared, you get the other version. So I don't memorize, I just memorize the first one, and then I can quickly create the other ones. So for us, since we have sine and cosine, we're going to be using this one for the first problem. Maybe for all of them, but if you see cotangent, cosecant pop up, or tangent and secant, then you're going to have to use one of those. Now, let's see. So sine is y over 2, and then you're going to square it. And then cosine is going to be x over 2, but then you got to square it, including division by 2 equals 1. So I'm plugging these into the Pythagorean identity, solving for sine and cosine in my head. And then x squared over 4 plus y squared over 4 equals 1. So this, you could call this an ellipse that has equal distance to both sides, but that special case is a circle. And we usually go ahead and instead of leaving a 1 on the other side, I mean, we could totally do this like we do ellipses and hyperbolas and just say, well, the square root of the number underneath them tells you how far to go in those directions. But you could also do this way. Say, okay, well, this is the, the radius equals 2. It's a circle. Now, I mean, you can make this graph bigger if you want to just kind of fill the space and kind of make each 2 increments equal a whole. So I'm going to sketch the circle first, the whole thing, but I'm going to do it lightly because it might not end up being the whole circle when we're done. So, but I think it's easier to sketch the whole thing once. Now, what we're going to do next is make a table, and this is just to get some quick, easy points. So 0 to pi. So if you plug 0 in, you get 2, 0. So this is the initial point, starting at the first time. And then if we plug pi in, that's going to be negative 2, 0. So that's over here. That's going to be the terminal point. And so now there's still a question, does it go over the top or does it go over the bottom? I think it's just going to be half the circle. So just picking another point in between those is probably going to make it much more clear. Cosine of pi over 2 is 0, comma 2. So we are going over the top. So this is the top half. So we're going to darken that in. Okay, and the direction goes from initial to terminal through the top. So we're going to draw a little arrow showing the direction. And so, that's it. Might write our answers and box them somewhere else. Like I like it all labeled on the graph, but I also like having it sort of singled out. Okay, so that's the first one. Next one looks very similar. Let's see if there's any differences. So it's going to be y over 3 squared plus x over negative 2 squared equals 1. And we're going to say x squared over 4 plus y squared over 9 equals 1. So that's your equation. This is an ellipse, or part of one. I'm going to go and sketch it. So we're going to go right 2, left 2, up 3, down 3. And the way we draw well, I kind of like to draw a box and then sort of use that as like my boundary. Okay. Might label the points, especially if you're not doing it with graph paper. I mean, I think it's just good to label your axis in some way or another to make sure, because I don't know, someone else might use two, increments for one unit, like we did last time. Now, make a little table, t, x, y, sort of pi. If you plug 0 in, we get -2, 0. So this is the initial point this time. So we're on the left side. And then when we go to pi, that's going to be +2, 0. So it's going to end over here. Terminal point. Go zoom in. It makes it easier to see. Okay, and we could plug a point in between, pi over 2. That's going to be 0, 3. So it does go over the top, like last time. But the direction is the other way. This is like clockwise instead of counterclockwise like last one. So initial point, terminal point, label them on the graph. Initial point was -2, 0. Terminal point was 2, 0. So there you go. That's the top half of an ellipse. Okay, next one doesn't have any trig in it, so we're probably not going to use trig. Probably going to use kind of like a substitution technique. Solve for t in terms of x is usually the way to go, because you're going to want y by itself when you're done anyways, right? So it'd be better to solve for t in terms of x and then plug that into there, and you already got y by itself. So y equals 2 times parentheses x plus 1 plus 3. So y equals 2x plus 5. So it's a line, or part of a line. So we're going to make a table. Now, I'm pretty sure it's going to be a line segment because we have endpoints. So we're going to plug t in, x, y, 1, 3. Plug 1 in, you get 0, 0, 5. Plug 3 in, you get 2, 9. Maybe plug 2 inside just to, I don't know. I don't think it's absolutely necessary in these ones, but I don't know. Might help you make your graph look better. So 1, 0 is, so 0, 5. 1, 2, 3, 4, 5 is right here. That's your initial point. I mean, we could just graph this line 5, up 2 over 1, up 2 over 1, down 2, back 1, down 2, back 1. And you could just graph it lightly. So, and then at time 3, 2, 9 is up here. That's your terminal point. Okay, so then we're going from there to there. And sure enough, 1, 7 is right there in the middle. The direction is from the initial to the terminal. So we're going to draw a little arrow. Our actual graph doesn't have any arrows on the ends because it stops. It's the line segment. Initial point, terminal point. So initial point was 0, 5. Terminal point was 2, 9. There you go. All right, next one. Let's see. This has trig in it. It's gonna be a little interesting, a little different. So we're gonna. It has cosine sine, so we're gonna use. Sine is y minus 2, and then it gets squared. And cosine is 1 minus x, and then it gets squared equals 1. Now, this is a circle. We'll probably write it like this. Now, 1 minus x squared is the same as x minus 1 squared, because you could take a negative out, square it, and it goes away. And that's just a little more friendly. So I'm rearranging the order and making things a little nicer. But that's a circle, right? With a radius equal to 1, and it's been shifted so its center is at 1 comma 2. So 1 comma 2 is the center of the circle. The radius is only 1, so maybe we should make, see if we could try and make these bigger. That's fine. We'll just do that. 1 comma 2 is the center. We're going to make a table. I mean, we could go and draw the circle right now. So it has a radius of 1. It's going to be a very small circle. I'm just drawing it lightly. Okay. Now, we're going pi over 2 to 3, pi over 2. Interesting domain. That's fine. So if you do pi over 2, cosine pi over 2 is 0, so you're going to get 1 comma 3. So 1 comma 3. Now, here's the deal. It should be on the edge of that circle. If it's not, something's wrong. So that's your initial point. And then 3 pi over 2, that's cosine is 0 again, so that's 1. And then sine is negative 1, so that's positive 1, 1 comma 1. Makes, at least it makes sense. It's on our sketch. Terminal point. Now the question is, it might just be the half of the circle, left or right half. So let's plug a point in between, like pi. And that would be positive 2. 2 would be right here. So it's definitely going on this side of the circle. And the direction is coming downwards clockwise. So there we go. All right, so initial point was 1 comma 3. Terminal point was 1 comma 1. There we go. Right half of the circle. Okay. Now, so far we've been talking about these parametric curves, but not so much in the sense of the motion of them. And but remember, these are supposed to be motion problems. So we're going to start to get a little more into that now. So here's an example of some generic curve x that has some function in terms of t, y that has some function in terms of t, different, has some endpoints a to e. So these letters on here are kind of representing different times, when time equals a, when time equals b. And so, the motion of this curve is going this way, right? It's kind of doing a loop-de-loop, which might seem crazy, but there's actually graphs that do that, and are parametric especially. So the question I want to ask is, I want to ask a couple different things. I want to know, what's the derivative of y with respect to x, which this is just regular old slope of a curve. Here's a curve. What's its slope? Positive. Now, and I want you to answer, is it positive, negative, 0, or undefined? That's the question. Just really qualitative answers, and I don't need any specific numbers. So, I mean, we can just take a look at that real quick and just say, well, this would be the slope of a tangent line. So it would be positive here. It would be undefined here because it's vertical, infinite. It's positive infinity, but that's not a proper answer. At C, it's 0. At D, it is also infinite, undefined. I would maybe think of it as like a negative slope because we're going down. E, that's just a negative slope. So, that's just regular slope. But I'm going to ask some other questions now about, we're going to break it down into dx dt. Now, dx dt, this is like the velocity in the x direction, right? is like Vx, and then dy dt is like Vy. So if we, now dx dt, we're taking the derivative of the x coordinate with time. So how's the x coordinate changing as time changes? So on this first one, the object is moving, so this is really left or right. If it's going to the left, it's negative. If it's going to the right, it's positive. Okay. And, and we're asking this as time progresses. So the first dy dx is, we didn't necessarily need to think about time so much. It's just the slope of a tangent. Now we're thinking about time. So at A, we're moving to the right. At B, we're not moving to the right or left at all. We're actually moving straight up and down. So it would be 0. It's not moving left or right at that instant. At C, we're actually moving to the left. D, we're moving straight down, so neither right or left. At E, we're moving to the right. Okay, now we're going to look at the same points and say, well, it's happening to the y coordinate as time progresses. And so now we're really just saying, well, how's the graph changing in just the vertical direction? So the vertical direction is either up or down. If it's up, we're going to say positive. If it's down, it's going to be negative. So on part A, it's moving up at an angle. At B, it's moving up, right? I mean, it's kind of like, is it infinite? It's definitely moving up. At C, it's not moving up or down, so it's 0. At D, it's moving down. And at E, it's moving down. So that's just kind of, so we're going to start to break these down. Now, here's another way to interpret dy dx, because, we were just looking at the slope of the tangent line. But dy dx can come from dy dt divided by dx dt. Because dy dx is saying, how does y change with x? Dy dt is, how does y change over a period of time? And dx dt is, how does dx change over a period of time? So it's almost like it's algebraic, even you could think, oh, it's like the dt's just cancel out and we get dy dx. So this is usually how we're going to find it, because we're usually going to be given parametric equations that have x and y separate. And we're not going to want to bother trying to find the Cartesian equation like we've been doing. And sometimes that'd be really hard. I mean, you could use that to find dy dx, but it's a lot more work if it's possible. So let's go to the back, and we're going to go. I want to just give you an example, and we'll ask some questions about it, and we'll start thinking more in terms of motion. Now I'm going to go ahead and just graph this. Usually we're not going to have this. We're not going to have this luxury, but we'll go ahead and use it right now as we're trying to figure out what this means. So we're going to go. We want our equation, our calculator to be in parametric mode just to make a parametric graph. We usually are not going to do this. And then y, I'm going to plug these equations in. So t minus 2 sine t, close, get rid of all the rest. Next one is 2 minus cosine t. Oops. Keep hitting the wrong buttons. Okay. That looks good. We need to go to window, and time is going to be 0 to 10. And I don't really know what the size of the graph's going to be. You could, I don't know, you could try and look at these a little bit and be like, well, sine's negative 1 to 1. T is going to get up to 10. So I don't know. I'm just try negative 10 to 10. Negative 10 to 10 first, just see what happens. So there's a graph, and it's doing these like little loop-de-loop things like I was talking about, and then it keeps going over here. Obviously, we could change your window to see this a lot better. So I'm going to say like maybe negative 1, up to, this was 10, so maybe 5. So I'm going to do negative 1 for x, negative 1 for y min. X max might need to be bigger. Y max could be like maybe 5. So See a little, we could probably make this graph even better, but looks pretty, and it just dead ends there. It's kind of interesting. I'm going to go ahead and make my window a little better and go y max is at 4. Okay. You guys should be good at quickly making adjustments to make your graphs look better. So let's sketch this, okay? So, so we went all the way to 12, and let's see, -1, -1. We went up to like 4, and the graph kind of does this. Looks like it starts at 1, and it kind of goes. Looks like it goes up to maybe 3, and so it kind of goes like this. Let's see, it goes like this, and then it kind of goes down here and goes like this, and it kind of looks like the graph is, maybe there's a pattern to it. Maybe it keeps going like this, maybe if we went backwards in time, negative time, it might do that. So it's kind of a pattern here. Now, if you look, so a lot of these things with, especially these graphs of trigonum, pi is a value where something happens, and it kind of looks like this peak is like at pi, 3, 4, 5, 6. It looks like this might correspond to 2 pi, and this might be 3 pi, which would be 9 point something, and then that almost kind of makes sense because this is maybe where the graph ends at 10 or something. I don't know. And that has to do with x being relying on t plus or minus some number. It kind of goes back and forth. So, so the graph starts here. This is the initial point, right? That we've been talking about. So this isn't a Cartesian. I think this would be impossible for us to get a Cartesian equation for. I don't even know if that's actually 10 or not. I mean, we could see later, but it looks like it's close to 10. So here's the terminal point, whatever it is. I'm not even saying we need to find it, but okay. Now, here's a question. Where is Johnny? Johnny was this fictitious character I used last year for some of the motion problems. So we talked about, when is he walking left or right or up or down. Now we're saying, when's he flying just horizontally? So horizontally would be totally left or right. And we could identify this on the picture and have a rough idea of when this happens. It might be here, and then looks like it's here, and then even here, and then maybe here. So there might be 4 different answers to this. Now, how would we figure that out? Well, one way is we could say, well, the slope of the tangent line dy dx would have to be 0. But more specifically, we know we're concerned about if he's completely horizontal, then dx dt will have whatever value it has to be, but dy dt would have to be 0. There couldn't be any change in the y direction. So this is kind of what we're looking for here, right? But you got to watch out. I'll talk about this more later. It's where dy dt doesn't, where dy dt equals 0, but dx dt doesn't equal 0 at the same time. Now it could, but what happens is we start getting into indeterminate form, and even if these are both 0, it might turn out that just one is 0 and the other is not, and you'd have to use L'Hopital's rule to figure it out. So dy dt, let's write the equation for it, is positive sine t, and we want to know, when is it equal to 0? Well, that's when time equals 0 plus pi k, right? Where k is equal to an integer. And so for us, if we're concerned with 0 to 10, that would be 0, pi, 2 pi, and 3 pi. 4 answers. Interesting. Okay. Now, confirming this, we're about to do some work that will confirm whether that's happening. Otherwise, you got to kind of watch out for it on your own. Now, vertically would be straight up and down, which would be right here, here, here. So I think there's 3 answers. And that would be when dy dx was undefined, right? that specifically is going to come from division by 0, which is going to happen when dx dt equals 0. So this is what we're looking for. But at the same time, we got to be careful where dy dt doesn't equal 0 at the same time. Now, if it doesn't equal 0, then clearly it's vertical. If it does, we just have to do more work to figure it out. Now, this makes sense that if you're going vertical, that there is no movement in the left or right direction, right? I mean, there's different ways to think of this. You can think of it as division by 0, or you can think of it as like there's just no motion in the left or right direction, so dx dt has to be 0. So let's find dx dt, and that's going to be 1 minus 2 cosine t. We're going to set it equal to 0. We get to solve a little trig equation. It's going to be positive 1/2, subtract 1, divide by negative 2. Reference angle, when does cosine equal 1/2? Well, cosine starts at 1, root 3 of 2, root 2 of 2, 1/2. So, we're probably going to be working in radians. So pi over 6, pi over 4, pi over 3 is the reference angle. And the quadrants, that cosine positive in quadrant 1 and quadrant 4. So then quadrant 1 is going to be pi over 3 plus 2 pi k. And quadrant 4 is going to be 5 pi over 3 plus 2 pi k. And so we're going to get pi over 3 and 5 pi over 3. And then also if we add this, give least common denominator, it'd be another 6. That'd be 7 pi over 3, which is about 7. So that's between 0 and 10. If we kept going and did this one, that would be 11 pi over 3, which I think, pi is about 3. So that's over 11. That's too far. Now, what would happen if these were both 0 at the same time is that those answers would come up in both lists. And if they do, then it's probably not going to be both of them. It might be one, it might be neither. And I'll let you know that the situation happens on some of these graphs that we're going to see. They're going to do something kind of like this, kind of have a cusp. And so if you looked at dy dx, it'd be like that, and it wouldn't be purely vertical or horizontal. Unless it was like this, then it would be. Or if it was completely sideways, it would be horizontal. But what happens at these cusps is that dy dx doesn't exist, and usually dx dt and dy dt are both 0 at the same time, so you have to do a little extra L'Hopital's rule work to figure out what the actual slope is. And another kind of question we might ask, we'll apply it to the same problem, is when does the object achieve maximum height or leftmost height? And so that's why we've been doing EVT lately. So max height would be max y value, right? And to find, that, we would say, well, dy dx equals 0, dy dt equals 0. This is how we're going to find our critical points. It also makes sense that relative max or min, which happen at critical points, are going to happen at a high point or low point, which is going to be when the object is completely horizontal in motion, which means the slope of its tangent line is 0, but it also means there's no motion in the y direction. If there's motion in the y direction, then you're not at a peak or a valley yet. So dy dt equals positive sine t equals 0. I mean, we already kind of did some of this work. T equals 0 plus pi k. So t equals 0, pi, 2 pi, 3 pi. So these are places, these are candidates to look at, but we also should check the endpoints. The endpoints are 0 to t, right? These are critical points. So we're just doing EVT like we've been doing. So I'd make a table, plug time in, and we're plugging them into the y equation specifically. We just care about the height. We don't really care about the x right now. 0, pi, 2 pi, 3 pi, 10. So we plug 0 in here, you get 1, you plug pi in here, you get 3, plug 2 pi in here, you get 1, you plug 3 pi, you get 3. Plug 10 in, it's not so pretty. 2 minus cosine 10. on my calculator, that is 2.839. Now from the graph, we're trying to find that max height. We can see it happens here and here. It happens twice at pi and 3 pi. So I already know what it is, but we're not going to have that lecture in the future. So, but it makes sense that our work did give us the maximum values at the places that we would expect based off this picture. In the future, we're not going to have a picture. Of course, we're going to answer this question. We could say the maximum height is 3 at time t equals pi and 3 pi. And then you could justify it by extreme value theorem checking endpoints and critical points. So I'm going to ask you guys to justify answers just like you always have, because you're going to get that kind of question on it for your response. Now, the other thing is we could identify the highest points, or maybe we could be asked for it. And the highest points are a little different. They're the XY coordinates, and we don't have the X values right now. So the X values, you'd plug pi into the X equation, and you would get pi for the first one, and then 3. And then the other point would be at 3 pi. If you plug 3 pi in, you also get 3 pi for the X value. And then the Y value is 3. So that could be a different question related to the same work and the same idea. Okay. And remember, these are X values. These aren't time values. It just happen that the X values end up being equal to time values at those points. How about leftmost? So this is a left to right motion. So this has to do with X, and furthest to the left is going to be the most minimum X. Okay, so we're looking for min X, and I think that's always good to kind of interpret this, in a more focused way. Okay, we're looking for minimum X coordinates, and that's going to happen when the slope is vertical, up and down, when dy dt equals 0. That's where we're going to find our critical points. That might have the answer. Now, looking at this picture, when is the graph furthest to the left? Right here. Right? So this is max y. This is max y. This is min x. Now, it's not going to, you might be, it's a negative x coordinate, but it's not a negative time. This is time 0 right here. This is actually positive time. It's just going backwards. Its motion's going backwards. So we're going to do similar work. We're going to find dx dt, which equals 1 minus 2 cosine t equals 0. We're undefined for critical points. So we're going to solve it. Cosine t equals positive 1/2. Reference angle is cosines 1, root 3, 2, root 2, root 2, 1/2, 0, pi over 6, pi over 4, pi over 3. Quadrants 1 and 4. So t is going to equal pi over 3 plus 2 pi k. And t is going to equal 5 pi over 3 plus 2 pi k. So the critical points are going to be pi over 3, 5 pi over 3. But then we talked about this last time. Also 7 pi over 3. And if you kept going over here, you would get a value too big. You get 11 pi over 3, and that's past the endpoint. So we're not going to consider that. So these are your critical points. The endpoints are the same as the last problem. So we're going to plug them in. We'll plug them into x. We don't care about y. So 0, pi over 3, 5 pi over 3, 7 pi over 3, and 10. So plug 0 in, 0. Pi over 3, sine of pi over 3 is root 3 over 2. So we're going to get pi over 3 minus root 3 over 2. The 2's cancel. And then 5 pi over 3 is going to be 5 pi over 3. And now this is quadrant 4, reference angle pi over 3, so it's going to be negative root 3 over 2, so it's going to become plus root 3. 7 pi over 3 is back in quadrant 1, so it's going to be minus root 3, and then 10 is just going to be something ugly. Probably need to use our, we'll see if we can get away without our calculator. Can we estimate these, if we had to? Like root 3 is between square root of 1 and 4. It's probably like 1.6 or 1.7. This is about 1. So this is definitely going to be something negative, whereas this is for sure something positive. This is about 7 minus 1.6. So this is definitely something positive. Sine can only be between negative 1 and 1. So this is definitely something positive. So this is enough right here to identify this as the midpoint without even having better values. Now, if you use your calculator, you get this. You get these values, which definitely makes it easier if you had to. But I might ask you guys to do it without a calculator. So this is the rightmost point right here at the very end, which makes sense on our graph. It just dead ends there. This is the leftmost point right here. So we're going to, now it says leftmost point. So this one is more specific, I think, the x and y coordinates, but we could write our answer. The leftmost x value is, and we want to use the exact values, pi over 3 minus root 3 at time t equals pi over 3 by extreme value theorem. By checking endpoints and critical points. Now, the actual point would be the x and y coordinates. So we already have the x coordinate as pi over 3 minus root 3, and then we plug pi over 3 into the y equation, and cosine of pi over 3 is 1/2, so it'd be 2 minus 1/2, it'd be 1.5, or 3/2 would be the point, leftmost point, x and y coordinates. Okay, so now to concavity. Now you can tell from the graph where it's concave up and concave down. We've already talked about that dy dx is dy dt over dx dt, and the second concavity comes from the second derivative. So we would take another derivative of the first derivative, which kind of makes sense, but this is not what you get. It would be nice if it was that simple, but it's not that simple. So I'm going to try and explain to you. This is the actual equation for the second derivative. Now, if we're talking about acceleration, we're going to take acceleration in each direction separately, and that's just the derivative of velocity. But this is the concavity of the graph. And so what we need to do is we have dy dx, and so we'll take the derivative of this again with respect to x. So we are going to do that. We are going to take the derivative of it with respect to x. But when we do that, that means, here's the deal, dy dx isn't going to have any x's in it. It's going to have a bunch of t's, okay? So what we have to do is we have to initially, so this is going to be in terms of t, right? Because when we get dy dt as t's, dx dt as t's, dy dx is going to have t's, but we're trying to take a derivative with respect to x. So this is like implicit, right? So we're going to go ahead and take the derivative of it in terms of the variable that it has, okay? Just take its derivative. But then we got to take the derivative of the variables inside with respect to x afterwards. So this is like, just as a as an example to try and connect the dots, it'd be like taking the derivative of this with respect to x, and you'd be like, well, derivative of y squared is 2y, right? But it doesn't have x's, so then you have to follow it up with dy dx. So that's the same thing here, is that dy dx is in terms of t, so we're like, well, let's just take its derivative. Just like when y squared just had y's, we're like, well, let's just take its derivative, 2y. But then the t's got to somehow be, we got to take its derivative with respect to x. Now, when you do this and you rewrite this, now here's the deal: we're multiplying by this, but what we could do is move it to the bottom. So it is dt dx, but the problem is that we'd probably be easier to do dx dt. So we move it to the bottom by division. So we change the multiplication of the fraction to division by a fraction, which is usually something we're trying to get rid of, but here it makes a lot of sense. You could try and memorize this equation. It is kind of gross, but it does make sense, and it might be good to kind of remember how to recreate it, because you might not use this that much, and it'll be easy to forget. So applying this to the problem that we were doing up above, we already found dy dt and dx dt, so I'm just going to go and use those. So dy dt was sine t, and dx dt was 1 minus 2 cosine t. So that's dy dx. And then we need to take the derivative of it with respect to time. So we're going to take the derivative of it with respect to time. And that's going to involve a quotient rule. Low d high minus high d low all over low squared. Gross. Okay, we try and clean it up. It's going to be cosine t minus 2 cosine squared minus 2 sine squared. And the bottom, I think I'm just going to leave like it is. Now here, this is minus 2 cosine squared t plus sine squared t. So if we factor the negative 2 out of there, that becomes a 1. And we get cosine t minus 2. So a little cleaner. So that's not the second derivative yet. That's just derivative of dy dx with respect to t. So then to get the actual second derivative, we got to take this result that we just found and then divide it by dx dt, which we've already used. So dx dt was 1 minus 2 cosine t, so it's going to be cosine t minus 2 over 1 minus 2 cosine t cubed, because there's already squared there, right? So this is your second derivative. So if we wanted to find the concavity at, say, time 2 pi, let's see what we get and see if it makes sense with our picture, which we're usually not going to have. So we're going to plug in 2 pi into here, and we're going to plug in 2 pi into here. Now cosine of 2 pi is 1. So this is going to be, that's going to be 1, that's going to be 1. So it's negative 1 over negative 1 cubed is negative 1 is positive 1, which means because it's positive, it's concave up. Now let's look at the graph and see if that makes sense. At 2 pi, we're right here, and it was definitely concave up at 2 pi, so that totally makes sense. Now for the assignment,